We begin our discussion of solar power with an exploration of how big of a resource solar power is. Before we get into that, we'll just review a little bit some of the resources available to you for learning. As a reminder, the Switch website is a great place to go to get some different takes on some of the energy information that we've been talking about, different explanations than the kinds of explanations that are provided in the textbook and that you get from me. So those are a great supplement if you want to go to those to help you understand some of what we're talking about. How much energy does the United States use and where does that come from? We've previously talked about this funny unit of energy. It's a gigantic amount of energy called a quad. Uh, it's 10 to the 15 British thermal units. And the US annually uses about 100 quads, 100 quadrillion British thermal units in a year. Of that pie of energy consumption, as you see here, about 80% are from fossil fuels, the oil, natural gas, and coal, about 9% or so from nuclear power, and about 11% total from the different sorts of renewable energy. And then the breakdown of that 11% is shown here. In 2017, only 6% of that 11% was solar. So 6% of 11% is about 0.66%. So less than 1% of our energy is coming from solar at the moment directly. As we'll see, wind and hydroelectric are indirect solar contributions. And here's another way of looking at that over time. At the top, you can see that the thickness of that green wedge is growing, but the total thickness of their energy consumption is growing as well. So let's take a look at how much energy is available from solar power. So to start off, let's go back and review this flow chart, which covers the sort of overall energy flows for the planet. And we are going to be coming back to this quite a lot over the course of the rest of the semester because it also factors in with how climate change works. Most of the energy arriving at the surface of the Earth, 99.98%, is coming from incident sunlight. Where does the other 0.02% come from? If you look down in the lower right-hand corner there, it says geothermal flow. That's where the remaining flow of energy to the surface of the Earth where we live comes from. So nearly 100% of all the energy arriving at the surface of the Earth is sunlight. Right off the bat, 30% of that is just reflected from the clouds, the atmosphere, and the land back into space. It just bounces off. It's not absorbed at all. 70% is absorbed in one way or another. And you can see that balancing that 70% absorption out is the 70% of infrared radiation, this big red upward arrow that says infrared radiation. That's 70% out plus 30% of reflected sunlight in the upper left. That's the energy balance. So the Earth is in approximate energy balance, the same amount of energy coming in as leaving. At the end of the semester, we'll see that currently the rate of energy coming in is a little bit greater than the rate of energy going out, and therefore the planet is warming up to adjust to that. So what happens to that energy as it cycles through the system of the Earth before it gets radiated away? Some of it just goes to making things warm. That 46% of that total solar flow, about 2/3 of that 70%, goes into thermal energy. That's the temperature of the surface of the planet. And it is that temperature which controls how much radiation goes away. Most of the remaining third goes into evaporating ocean water. So it takes, as we saw back in module 3, I believe, on heat, that it takes energy to convert water from a liquid state to an evaporative state, to a gaseous state. And that energy comes from sunlight, which goes into that water, causes that water to evaporate. So that means there's stored energy in the water vapor, which ultimately is radiated back out into space. Tiny little fraction, 1%, goes into driving the flow of the oceans and the flow of the atmosphere as wind. An even smaller fraction, less than 1/10 of 1%, is absorbed by plants and used as through the process of photosynthesis to make complex organic molecules. That is what provides the uh, chemical energy supply that we live off to keep our bodies alive. Uh, some fraction of that chemical energy gets buried and over time accumulated as fossil fuels. Uh, so this is showing the sort of overall flow of solar energy through the planet. And then there are these tiny amounts over here on the right, tidal energy and geothermal flow, which we've mentioned, but we're not going to have time to go into in much detail at all. So now let's talk about just how much energy is it that's coming from the sun. So if we went up in space above the surface of the Earth and had a 1 meter square collecting area and pointed it straight at the sun and could measure the energy of the photons of light coming through that meter, there would be 1,360 joules of energy in light coming through that meter each second. So that's 1,360 watts per square meter. That's indicated by these orange arrows on this. And then if we say, okay, well, what's the total amount of energy hitting the Earth? I have to look at the cross-sectional area of the Earth, pi times the radius of the Earth squared, and I can get that total amount of energy. So there's some example problems that work through that. Now, at the surface of the Earth, depending on where you are, your square meter is not pointing straight at the sun. So if you're closer to the poles and you set a square meter of ground or ocean down, it's pointing up at the sky, but the sun is off at a lower angle, and therefore the number of those arrows coming through there is less than if that square meter were pointing at the sun. So there's an effect of the latitude that controls the local amount of energy that you would get per square meter of ground. But this value of 1,360 watts per square meter is called a solar constant and is a value of the amount of energy arriving at the Earth from the sun. So remember on this previous slide, 30% is reflected. A lot of that reflection and takes place in the upper atmosphere, and there's absorption in the upper atmosphere. So if you actually are down at the surface of the Earth, that 1,360 drops down to about 1,000 watts per square meter. The total amount of energy absorbed, I'm using the area of this circle that's shown in the middle here of the Earth. It looks like a very skinny egg. That's pi r squared. That's the total amount of sunlight blocked by the Earth. That's pi r squared. But the area of the entire surface of the Earth is actually the area of a sphere, which is 4 pi r squared. And that means that we only get about 1/4 of that 1,000 watts per square meter on average, if I average taking into account the curvature of the surface of the Earth and daytime and nighttime. Obviously, on the night, that whole half of the Earth is not absorbing any sunlight for half the time. So the combination of those two effects drops the average insolation at the surface of the Earth down to 239 watts per square meter. That's taking into account absorption and reflection from the atmosphere and day and night and the effects of the curvature of the Earth. So if we say, well, 239 watts per square meter, how much energy is that? It's not a huge amount. Here's an example of a sort of concept vehicle optimized to try to get as much solar power as possible to drive the car. And that has a peak power of 7 kilowatts. That's 1,000 watts per square meter at noon and 7 square meters of surface area on the car. And there's a video in this module that shows the amount of electrical power used by my electric car when it's driving, and it goes up to 50, 60 kilowatts. So 7 kilowatts peak, and I'm not driving like crazy or anything. So 7 kilowatts peak power is not a lot of power directly available there. So the solar energy is spread out a lot. If we now take a look at what it looks like over the course of a day, obviously highest at noon. The two curves here, the blue curve is a perfect cloudless day. The red curve shows actual measurement from the book's author's solar power system at home, and those dips are just due to clouds. So it was cloudy in the morning there, and it was clear after about 2 p.m. You get different amounts of radiation from the sun at different latitudes. If you are moving towards the pole, then you get no sunlight in January. That's the solid black line, but you get a very large amount in the summer because the sun never sets there. And then in the mid latitudes, where you see the cities labeled, you get solar power throughout the course of the year, but a greater amount in summer and a smaller amount in winter. And the differences between summer and winter vanish as you approach the equator. And Florida is about where that vertical dashed line is. And so you can see that there's a factor of 2 or so difference between the amount of sunlight hitting in the summer compared to the amount hitting in the winter. And there's some graphics in the module showing my own solar photovoltaic system at home and the difference in the amount of production that I get in December compared to May. So we had this average 239 watts per square meter. There's just some examples of different cities, a little bit lower than that because they tend not to be concentrated near the equator. If we look at the United States in particular, you can see that the greatest amount of the solar resource, the highest concentration at least, is in the desert Southwest, and the lowest is in the sort of Great Lakes area. Florida, although it's the Sunshine State, has a lot of cloud cover in the summer months, and so it's better than some regions of the country, but it's not the greatest because of the cloud cover. The last item to mention here, before we move along to some examples and you see just how much energy is available from this roughly 239 watts per square meter averaged over the surface of the Earth, is a reminder of what part of the visible light spectrum sunlight comes in. Light is made up of different wavelengths, that means different colors. Sunlight is brightest in the visible part of the spectrum where we can see. That's no coincidence. It would be not very useful if our eyes had evolved to see light that the sun is not bright in. But there's a significant amount of energy that is coming from the solar spectrum that's outside our ability to see it in the infrared and in the ultraviolet. But about half of the solar energy is in the visible part of the spectrum. So in the later components of this module, we'll be seeing how much energy is available, the technologies to convert it to useful form, and how that compares to what the human requirements are for energy.